Okay, hi guys. Here's my attempt at making a doc style video. Alright, so the last ed puzzle that I assigned for you from doc was on a solenoid. And I just want to go briefly through that again because there are a few points that I want to make sure that you get. Okay, so this is the solenoid. It's got a current coming in, current coming out. It's a loop of wire. So part of the thing that's kind of tricky here is imagining this three-dimensional situation. So as he showed you, he had like an actual solenoid, which all of mine are back at school right now. So we're making do. It's a coil. So you look here, right? And you see the coils going like this, right? Coming in, and out. Okay, so here, so it's, in, out, in, out, in, out. So the idea is sometimes we just like to draw it like this. So we're imagining it going in and out of the page. We kind of like just took a little chunk and slapped it in half, all right? So we see the current going into the page, out of the page, in, out, in, out. Okay, so if you look at each one of these currents, right? We've done this how many times now with the right-hand rule? Put our thumb along the current. Our B field is in concentric circles around that guy, right? So this is what they end up looking like. Like that and like that. Like boom, boom. Right? This was all just the current from each of these. Okay. You can do the same thing up here. We get thumb. Here's our magnetic field. So it looks like that. So swoosh, 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 swoosh. Okay. If you look in between each of these guys, what is happening right here? We have a little magnetic field from this guy this way. We have magnetic field from this guy this way. So what happens? Schwa, right? They go away. So there is no B field in between these. Okay? There's some B field out here, but as you remember, these kind of go like this. They get weaker and weaker as you go further away from the wire, right? So eventually the B field will drop off. And then we'll take, of course, a limit for an ideal solenoid later, and we'll talk about that. But what is happening inside? So this guy goes like this, 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 and this. This guy goes like, that. All of those are going this way. So what we end up getting is a net B field inside the solenoid that looks like that, okay? And if you want to know a quick, cute way of figuring out that B field, the direction of that B field, and this is something that was not in the other video, if you hold that loop so that your fingers, I'm going to stand up for this, your fingers go down here and up here. Look at my thumb. What's my thumb doing? It is right there in the middle, right there along B. So if you hold that wire and that's how the current goes, there's your B field, is that direction. It's pretty cool. Right-hand rule works in like a gazillion different ways. So anyway, let's actually use this solenoid to actually calculate that B field, because it ends up being very, very cool, because the B field inside a solenoid ends up being uniform. Okay? And that's a very nice, useful result. So I'm going to do this. Just sketch this out again. Okay. So that's our cutoff. That's our cross section of a solenoid. So I'm going to draw an Amperian loop. Okay. So let's talk about what that means. I'm going to give it a direction, and I'll talk about the direction in a second. Okay, we're talking about Amperian loops. Why are we talking about Amperian loops? Because Ampere's law looks like that, okay? So we have seen this symbol before. We saw that in Gauss's law, okay? And Gauss's law was that integral with the circle, and it was dA. So that meant a surface integral over a closed surface, right? So that Gaussian surface, which was, remember, an imaginary surface, was a surface that we did this integral over, and it enclosed a volume. This is dl. This is called a line integral, and we are going to do it over a closed line, which you can just think about as a loop, okay? So that is your Amperian loop. And just like Gauss's law, we choose, or Gaussian surfaces, I should say, we choose Amperian loops to make our life easy, okay? So when we chose Gaussian surfaces, we chose them so that the electric field was either constant or zero on it when we were doing the integral. Here, we do the same thing. There's one extra thing about Amperian loops that you might notice. Gaussian surfaces were all like gorgeous little symmetric, spheres or cylinders. Amperian loops are occasionally just circles, but they can also be like rectangles. And we do that, it's still a closed loop, right? But we do that so that it has interesting or useful values of magnetic field along each of the sections. Okay, so let's do that. Let's label these sections. Let's call that L1, that's L2, that's L3, and that's L4. Okay, so up here we decided like where we had a B field, and maybe there was zero some places. So hopefully you see that along L2 and L4, right, that was here, there was no B field. So that's going to be useful. Okay. Let's just write that out in more explicit terms. Okay. All right. How about B1 L1 plus B2 L2 plus B3 L3 plus B4 L4 is mu naught I enclosed. I did something super fancy and loose, fast and loose, sorry. What did I just do? That was a dot product, guys. But then I took it away. Oh, did I just cheat? I don't know. Probably not. Probably we choose these Amperian loops so that, we don't have to worry about that dot product. Because think about it. Let's get a pretty color for our B field. What did I use? The green? Our B field was here, right? And look at that B. And then, remember how I said that I chose a direction? Okay. You have to choose a direction when you do these line integrals. So you're saying, I'm going this way, this way, this way, this way. Okay. So look at my B and look at my L, right? They're parallel. So the dot product, boom, nothing. Okay. B2 is 0. And B4 is 0, right? Groovy. What about L3? Look at this section. So this is where I get to have a little bit of fun. And I get to make the argument that B3 is 0 if I take that L3 section to be infinitely far away. Okay? So I want you to imagine, this thing all the way away, right? The B field is 0. Okay? If you go really far away. Cool. So that's lovely. So cool. We're looking pretty good now. So B1, I'm just going to call this little section, right? We call that L1. Cool. I'll just keep that. That's mu naught. And then let's talk a little bit more about what this I enclosed could be. So here's my loop. And so I have these 3 dots in the loop, okay? Each of those dots has a current I, all right? So I have how many of those dots? Let's call it n. I have n dots, so I have n times I, right? Where n is the number of turns, okay? So my magnetic field inside of a solenoid is going to be this. I'm going to write it like this, and I'm going to describe what I just did in a second. Okay, this little n, right, if I divide that n over that length, it's the number of turns per length. It's kind of like a turn density, if you will. Okay? But this guy is on your equation sheet. Okay? So that's useful. And it actually says like B sub S for B of the solenoid. So I want you to notice a few things. Okay? It is independent of how those turns look. So independent of the radius of the solenoid. So that's really interesting. And then the one thing that I want to tell you is this is true for an ideal solenoid, which means the total length is much greater than that radius. And in that case, we can actually say that B equals 0 on the outside of an ideal solenoid. Okay, and I'll stop there.